Okay, hello everyone. Guess we will give everyone a couple of minutes to join before we get started. But if you want to do an audio check or any other last minute configuration checks, now is a good moment.
1, 2, 3, checking.
Yes, your audio is working, Carsten. Thank you.
Thank you.
Okay, now I see more people have joined, so let's get started here. So welcome everyone. This is the Think to Think Research Group interim meeting. My name is Ari Keränen and the co-chair Carsten Borman also here. Quick reminder on the note well, as always with the IRTF meetings, the note well applies. So if all goes well, you will be recorded. Be nice and professional with each other, and the IPR guidelines of the IETF do apply. There's a longer version of the note well in the chair slides. You're very welcome to check them out or ask from the chairs if you need any more information. Also, quick reminder of the goals of the IRTF. So this is an IRTF meeting, and here we focus on the long-term research issues related to internet. So we are not a standards development organization. That work is typically done on the IETF side, but of course we do work closely with many of the IETF working groups and participants. But when it comes to actual standards development, it should happen at the IETF side. On the admin side, as usual, we have our interactive notes, and welcome everyone to join taking notes. And I see already someone joining there. Thanks a lot. Thanks a lot, Marco. If you're not already on the mailing list, please do join. That's where you get the best information of all the ongoing and upcoming activities on the Thinking Research Group. And we do have our usual GitHub repo for the latest information of the meeting. Also, a quick reminder of the upcoming meetings and activities. We will have a face-to-face summer meeting at the IETF at the end of July in Madrid. We will plan to have this typical overview of the ongoing activities, but also deep dives on selected topics. For example, it's going to be a very interesting talk on security topic upcoming, a bit longer version from the interim that we had and going a bit more details. So I very much welcome everyone to join. But we're also still open for more agenda items. So if there's something you'd like to present in the Thinking RG meeting, please do let us chairs know. More information is already on the mailing list. In addition to the user summary meeting, we'll of course have the traditional hackathon activities. There is already an SDF and NIPSI project proposed in the hackathon, which many of us in this group will probably be taking part of. Then we'll also have today a demo of this lightweight and SDF matter bridging. That's another potential topic for hackathon activities. But of course, as usual, open for more topics around the scope of the Think RG. So if you're planning to organize something, let us know. Very happy to cooperate there, and probably we'll be sitting in a common table at the hackathon as usual. Then our agenda for today. Now we're at the interface, almost done here. Next, we will have Niklas Meyer presenting this SDF informed bridging between lightweight and matter with a demonstrator. After that, Carsten Bormann will follow up on the derivation and instantiation, two dimensions of model evolution topic. And we also have a bit of flex time if you have some ad hoc topics, or if you want to go over time, this time we have a quite relaxed agenda. So feel free to go into the discussions and propose if there's something you want to cover. Any questions or comments on the agenda before we get started? Okay, hearing none, I can share your slide, Niklas, and I will give you the right to change the slide control. Now it should work for you.
Yeah, let's see. So I probably want to share my own slides because I've made some small changes to them. That
Absolutely,
should
go ahead.
probably not be a problem. So let's take a look. So let's take a
I think you switched off your audio. Can you still hear us?
Yes, I tried to drag and drop my presentation. Not a good idea, but let's see.
You will have a demo anyway, so maybe you can do the screen sharing.
Yeah, I also think that screen sharing might be more suitable. So let's do screen sharing. Hopefully my Firefox is a bit more stable today, but it should work. So.
That didn't quite work. Can you press the screen share button again?
Let's try again. Request screen share. Yes. So let's see. Laptop screen. This one. Perfect. So yeah,
Looks
perfect.
Good.
Perfect. Yeah. Well, let me just turn on my camera because that might be important. So I'm gonna have to use my laptop camera as the other camera is, for whatever reason, not recognized by Firefox. But that should also not be a problem. So yeah, welcome to my presentation. Today I'm going to present about SDF-informed bridging between lightweight machine-to-machine and Matter. So, wrong screen. So starting firstly with a quick little introduction into Matter. What is Matter? Matter is a relatively new IP-based connectivity standard that is specifically designed for use inside the smart home, and that has, next to other goals, the central goal of increasing compatibility of different devices from different manufacturers. For its data model, Matter features a hierarchical data model structure with so-called nodes at the top of the hierarchy. These nodes are the top-level addressable units, and typically a Matter device only has one of these nodes. These nodes consist of one or more endpoints, which in itself consists of one or more clusters, and clusters are a collection of attributes, commands, as well as events. On the other side, we have lightweight machine-to-machine, which is also a standard meant for machine-to-machine communication and is designed to be used in the context of the Internet of Things. Furthermore, it features support for multiple application layer protocols for communication, namely being CoAP, MQTT, as well as HTTP. For its data model, it also features a hierarchical structure with the data model of a singular lightweight machine-to-machine device consisting of one or more objects, which in itself consists of a collection of resources. Given these two data models, I initially set out to create a mapping between those two data models. And I accomplished this task by using the semantic definition format as an intermediate. As you can see in the table below, we have the three data models next to each other. On the left side, the metadata model. In the middle, we have the semantic definition format, and at the right, the lightweight machine-to-machine data model. So you can see that in the metadata model, a node gets mapped onto an entire SDF model, which gets for lightweight machine-to-machine mapped onto a lightweight machine-to-machine device, so an entire device definition. An endpoint in the metadata model gets mapped onto a SDF thing, which then gets mapped onto also a lightweight machine-to-machine device with a little asterisk, as technically the lightweight machine-to-machine data model is not really expressive enough to be able to represent the complexity of a SDF thing. But for especially for my use case with the metadata model as a matter a matter device definition typically results in one SDF thing inside the SDF model, I've made the small assumption that the ASDF thing also represents the entire lightweight machine-to-machine device if one is present. So next to that, for clusters, these get mapped to SDF objects, and in the lightweight machine-to-machine world get mapped to objects. And lastly, we have attributes, commands, and events, which get mapped to accordingly SDF property, SDF action, and SDF events. And on the lightweight machine-to-machine side get mapped onto different kinds of resources. To showcase a bit more clearly how such a abstract mapping would look in the real world, I've brought with me a little example conversion that showcases how such a mapping would look when actually converting such device definitions. So at the left side, you can see an original matter device definition. This is split into two parts. So at the top, we have the so-called device type definition. In the meta world, a device type definition defines an entire endpoint. And this device type definition also lists all the clusters that are configured on a certain endpoint. So that's why below we have the only cluster that is configured for this endpoint, and that is the on-off cluster, consisting in this case of a attribute, the on-off attribute of the type bool, as well as a single command, which is the toggle command. So when converting this matter device type definition to, on the right side, a SDF model, we can see that the device type definition up here gets mapped onto a SDF thing, as we can see right here. These elements here, those mandatory conforms in the meta world, they mean they're used if a element in the data model is mandatory. So if it's required, if it always has to be there. That's why these get translated, as you can see here, into SDF required elements. Oh, too fast. So, back to the slide. So the cluster below here, as you can see, the cluster gets translated to a SDF object with its according attribute being mapped to a SDF property, as you can see here, with all of its fields. So type, Boolean, default value, nullable, readable. These elements all get mapped. And below here, we can see the SDF action, which before was the command right here, mapped into the SDF world. So let's take a quick look at how this SDF document, this SDF model, gets mapped into the lightweight machine-to-machine world, and hence the or target definition. So as we can see here, the SDF thing, as I've said before, in this case, because this SDF model contains a SDF thing, this SDF thing actually represents the entire lightweight machine-to-machine device. The SDF object gets translated into a object definition in the lightweight machine-to-machine world. That's what we can see here. This is the on-off cluster from before, with the SDF property as well as the SDF action being translated into two resources. Here we have the resource that represents the original SDF property with also according, for example, here we can see the read operation. And below we have the toggle action accordingly with its execute operation. So given this theoretical conversion of these data models using SDF as an intermediate, how did I incorporate this conversion into the concept of the bridge that I will also be demonstrating today? So the general assumption, the general idea for this concept of a bridge that will in the end be able to establish communication between Matter devices and lightweight machine-to-machine devices is that the bridge will need to do two things. So we have the initial step, which is the initial conversion, meaning we have to take on the Matter side, the Matter device definitions for all Matter devices that want to communicate with lightweight machine-to-machine devices, and we have to convert their respective data models into a lightweight machine-to-machine compatible representation. And for the other side, we also have to take, for every lightweight machine-to-machine device that wants to communicate with a Matter device, have to take its data model, so its device representation, and convert it accordingly using SDF as an intermediate into a Matter compatible representation. The second step that the bridge will need to do after this initial conversion is it needs to enable bidirectional communication by supplying functions that are able to live translate interactions between Matter as well as lightweight machine-to-machine devices. To go into a bit more detail about how this is accomplished, let's take a look at the Matter side. So how is this bridge theoretically implemented on the Matter side? So we have our two steps again, the initial conversion. So we take the definition of a lightweight machine-to-machine device, we convert it into a Matter compatible representation. And from this representation, we can generate a new endpoint, which can be used by other Matter devices as a communication entry point for communicating with this lightweight machine-to-machine device. So this endpoint will later be used to enable bidirectional communication with other Matter devices. What we also have to do is, based on these informations that we got from the conversions, we can set up internal translation functions that I will later showcase in a bit more detail as part of the demonstrator.
Niklas,
yes?
We have one person in the queue. Is it okay to take questions now?
Yeah, of course.
Okay. So Michael, go ahead.
When high-level concept, maybe the word bridging is the wrong term, and that might confuse people. But on that topic, actually, in the examples, is the device, the target device that's going to be controlled, light switch on off, is that on the L2 M2M side, controlled from Matter, or is it the other way around? I imagine you want both, but what are you talking about specifically now? Which direction?
Both. Specifically both. So the example that I showed is for one direction, as my proof of concept has in both directions a simple light and switch example, and that would result in pretty similar conversion results if I would convert the lightweight machine-to-machine device definition back into Matter. That's why I left it out, just for simplicity. But the bridge actually is targeted at both directions.
Right. So I'm just saying it's maybe more a gateway than a bridge. And some people in various layers of the stack may get confused by that term. But right now your switch, your actuator your sensor, which is your light switch, is on the Matter side, and your light bulb is on the M2M side.
No, not.
No, it's the other way
On the
around.
Matter
Okay.
side, we have a light switch and a light, and on the
Okay.
lightweight machine-to-machine side, we have the same. That's why I
The same
use the
thing.
term
So they
bridge.
can control in the whole X of the whole.
Yes,
Okay.
exactly.
Just thanks.
So let's continue and let's look at the lightweight machine-to-machine device of the functionality of the bridge. So for the lightweight machine-to-machine side, we also have to generate a lightweight machine-to-machine compatible representation. This is also done via the initial conversion. So we take the Matter definitions of all the Matter devices that want to communicate to the lightweight machine-to-machine devices and convert their definitions into a lightweight machine-to-machine compatible representation. For my proof of concept, I've chosen to use CoAP as the application layer protocol. Hence why I opted to generate a CoAP server resource that deploys the converted lightweight machine-to-machine compatible representation of the Matter device for the lightweight machine-to-machine device to be able to communicate with. Additionally, I also implemented a simple CoAP client that will be used to communicate with the lightweight machine-to-machine device. As before, based on the informations that I got from the conversion process, I was also able to set up in this process the internal translation functions that are responsible for the live translation of interactions between the devices. So how does the proof of concept actually works? How does this theoretical construct translate into the real world? To find this out, I built a small proof of concept. On the left side, you can see a little network diagram showing how these devices theoretically communicate with each other. As you can see in this network diagram, 3 of the microcontrollers that you can also see on the right side in the picture are using Thread for communication, and one of them is using Wi-Fi for communication. If you look at the picture on the right side, you can see the 4 devices that were chosen to construct this proof of concept. We have a Matter switch, a Matter light, the before mentioned bridge, as well as our lightweight machine-to-machine node, which is actually a combination of a switch and a light in one device. So let's get to the interesting part, and that is the demonstrator. So let's first take a look. Let's actually get to this slide. One thing that is also pretty important for this proof of concept is, as you can see in the network diagram, we additionally have a Raspberry Pi. This Raspberry Pi is hosting a co-op server, and it is hosting all the files that the bridge needs. So all the conversion files that the bridge needs to be able to start the conversion process, these are all hosted on this Raspberry Pi. So let's take a quick look at the Raspberry Pi. Just quickly look. So as you can see here, in the background, I've already started the bridge, and we will take a look at the bridge in a short moment. But as we can see here, this is the bridge that I've built, and it accordingly gets all the required files from this corp server implementation. So let's take a look at the more interesting side, and that is the bridge. So this is the serial output of the bridge, and we can go through here. So let's take a look at what the bridge is actually doing before I showcase the microcontrollers interacting with each other. So let's take a look. So
Niklas,
this above, yes?
is it possible to increase the font size a little?
Yeah, probably. Oh, let's take a look. Oh,
Perfect, thank you.
this might be better. So the first part here is not that relevant for us as it's part of the standard implementation of Meta. That's the initial part that's interesting for us happens right here. So as we can see, what the bridge does, it is loading the initial SDF configuration files. So let's take a look. Why does it load an SDF model as well as a SDF mapping instead of, in this case, this represents the lightweight machine-to-machine device, instead of a lightweight machine-to-machine definition? So this is one of the limitations of the current implementation of the proof of concept. Simply because of the at the time of constructing this proof of concept, there sadly wasn't a SDF to lightweight machine-to-machine converter available that was able to run on these microcontrollers. That's why the lightweight machine-to-machine to SDF conversion had to be outsourced, in this case to the Raspberry Pi, which does the conversion process and provides the converted SDF model as well as SDF mapping to the bridge. In the next step, you can see that the co-op client finished loading the configuration files, and it starts the conversion process to convert this SDF model as well as SDF mapping to the meta world. It completes the conversion process, and afterwards it starts to deploy the converted meta device. So here you can see it's creating the custom endpoint that will later be used by other meta devices for communication. It's right here, it also loads another configuration file that is not very relevant for us right now. This is part of another complication that I stumbled upon when implementing this bridge, and is caused by a very static implementation of the Meta C++ implementation of the Meta standard, but I will get to that at a later time. So let's just skip past this XML and look down here. As in the background was the bridge.
I lost the audio.
Same here.
He's frozen.
See, what happened is he turned the power off to his desktop using his L2TP as a M2M. Maybe, I don't know, does Bremen have any power? Maybe all of Bremen is out. That, you know.
At least I cannot confirm that.
It's a classic demo effect.
I don't know why it crashed. Let's try to resume. So, yes. Let's try again.
Welcome back.
As I've said before, my Firefox is not that stable at the moment, and I don't know why. So let's continue. So as I've said before, at this point, the Matter side for Matter devices to the side of the communication is deployed. What the bridge actually does in the next step is, instead of directly deploying the lightweight machine-to-machine side, is it firstly creates the needed live translation functions. So that's why it's loading these two documents also via co-op. And let's take a quick little look at what these JSON documents actually contain. So what the bridge needs to set up the live translation functions, it needs to know if I get, for example, a request on this cluster with the ID 6, for example, and on the command with the, for example, the ID 2, it needs to know, okay, which ID is that in the lightweight machine-to-machine word. So we need a mapping between lightweight machine-to-machine IDs and as well as Matter IDs to enable this bidirectional communication. That's why you can see that this mapping contains lightweight machine-to-machine IDs as well as Matter IDs. These are also a result of a direct result of the conversion process, as these are outsourced as part of the SDF mapping, and these are used at this point to generate this mapping so we can set up the bidirectional communication. So let's take a quick little look at the last part. So the last part is the lightweight machine-to-machine device. So what the bridge does, it creates a co-op server. If we take a quick little look down here, we have the converted for the Meta device, the converted lightweight machine-to-machine compatible representation that gets loaded. As I've said before, in this case, it loads this definition directly instead of converting it on device, as I have the limitation of no converter being available for use on the microcontroller. That's what you can see here, the familiar on-off cluster of the Meta device that will be bridged, converted in this case into a lightweight machine-to-machine representation with all of its resources. And in the end, we can see that the custom resource was successfully created right here, and the co-op server was started. So how does this translate into an actual interaction? And for that, I'm gonna... So let's take these. So what I have behind me right here, hopefully maybe a bit small, but this is the lightweight, the bridge implementation that we've seen from before. This is the microcontroller right here. And these let's take a look. These are the microcontrollers, also from the picture of before. These two are Matter compatible devices, and this is the lightweight machine-to-machine device. So let's take a look what happens first for the Matter side. What happens if this implementation of a meta switch wants to communicate with this lightweight machine-to-machine device. So let's take a look. So what do we see here? This top part is the Matter side. So that is internally in the bridge, how Matter computes the request coming from this microcontroller. And this is translated using the live translation functions into an according corp client interaction. In theory, this LED should have gone out, but in the real world, it sadly the implementation of I/O on this microcontroller especially is a bit crap. That's why oftentimes this LED just does not want to turn on or off. But still, we can see the communication between these microcontrollers. So what the Matter controller tried to do is it tried to toggle this LED. And how toggle is implemented apparently on the Matter side is in two operations. So we have a coop get request, which gets the current output status, so is the LED on or off, from the lightweight machine-to-machine device. And afterwards, what the Matter device, with this given this information, tries to do, it tries to deactivate this LED by writing accordingly to the resource on the lightweight machine-to-machine device. That's what we can see here. Writes a 0, which, as you can see, does not translate into the LED flash because this implementation is not that great. But let's take a look at the other side, which should function with the LED. Let's take a...
Maybe you can try to stay in frame.
Oh yeah.
Adjust your camera a little bit.
Yeah,
so it's easier
multiple
for you.
screens. So yeah, I'm trying to. So let's take a look. Let's wait for a little moment as this microcontroller actually does 3 separate interactions. And let's take a look what happened right here. So as you can see, the LED on this microcontroller, this was out before. This is now lit. This is the Matter device, the Matter light. And as you can see, what this implementation of a lightweight machine-to-machine device does, it sends a request via its Corp client to the Corp server implementation on the bridge behind me for the object ID 42770 and resource ID 8. The translation functions translate this request to a request for cluster 6 with command 2, which is the toggle command. That's why you can see the microcontroller toggled its LED. And as part of my proof of concept, I've also implemented 2 other requests that the lightweight machine-to-machine device does. It writes to one of the attributes of this of the Matter device. In this case, it writes the value 20 to cluster 6 with this attribute number. Yeah, that's what you can see here. Write request. We get the response from the Matter implementation that the write to the attributes was a success. The write is done. And at last, what it also does as a quick little test is it tries to read from an attribute on the Matter device. In this case, it tries to read the attribute 0 of cluster 6, which also results in a success. So, given this quick little demonstration of how this demonstrator works, let's get into the last part, which is the evaluation of the proof of concept. As you've seen before, this proof of concept comes with a few limitations. Namely, one of the biggest one is that the C++ implementation of the meta standard that I used is for use as a bridge not very flexible, meaning that bridge devices, so devices that need to be bridged, especially their functionality theoretically needs to be known at compile times, because what the Matter C++ implementation does, it generates structs and different objects at compile times that are compiled into the firmware and later enable the bridging of devices. So these information theoretically need to be known at compile times, though I showed as part of my proof of concept that this limitation is more of an artificial limitation, as I was able to make most of the functions that enable this bridging behavior. I was able to make most of them more flexible in a way that they could work with the informations given by the conversion process and didn't need the exact device functionalities to be known at compile times. Secondly, we have a limitation of a high resource demand. The example that I've shown is relatively simple, meaning we have simple on-off devices, a simple switch, as well as a simple light. And with this example, I did, even though it's fairly simple, I did get into the limits of the microcontroller that I used, namely, especially memory consumption, which was namely caused by the XML as well as the JSON parsing. So given these, how would some possible future improvements for this proof of concept maybe look like? One of the possible future improvements for this proof of concept, for the concept of such a bridge, would be a mechanism for auto-bridging devices. Currently, a user would have to manually find two devices that want to communicate with each other and manually establish the bridging between them. So future mechanisms could maybe automate this finding of microcontrollers or devices that want to communicate with each other and establish such bridging automatically. The second thing is complete on-device conversion. As I've said before, sadly, currently, complete on-device conversion was not possible due to a lack of a converter for lightweight machine-to-machine and SDF. So in the future, the complete conversion process could probably happen on the bridge. Alternatively, we have the alternative of outsourcing this conversion process, especially for more complex data models or more complex device definitions, as these can get pretty complex and pretty large, to an external service in the style of conversion as a service. And that's it. That's my presentation. If you've got any questions, feel free to ask.
Hi again. So a couple different questions. One of them is, so to what extent was your gateway entirely driven by the SDF, or did you wind up having to tweak bits of code to make it work?
So one of the main things that I had to optimize to get this running on the microcontroller was I had to optimize the libraries used for XML as well as JSON parsing to be very particular for the JSON files and the XML files, especially their sizes that were used in my example.
So I'm really a bit mystified by why you're trying to fit that piece into a microcontroller. I guess I would have thought that it would be living in kind of, smart speaker, home router, and NAS or something like that. which would actually have the multiple physical interfaces that you need. So I'm just wondering why you were so concerned about getting it in a microcontroller for the gateway service itself.
Definitely. So that was one of the results of this whole proof of concept was, is it possible? Yes, it's technically possible. Is it advisable? Probably not. So the alternative of conversion as a service is probably the better route for the future of such a bridge.
And I was thinking about conversion as a service given to an SDF model and I guess two target models devices. I'm imagining a conversion as a service that doesn't actually do the conversion, but rather writes a, I don't know, Lua script or something that loads into your, or MicroPython script that loads into your converter, and then which then has, you know, a good XML, JSON, blah, 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 hard-coded library. And the Lua actually, or whatever, Python actually does the mapping, you know, as, I don't know, it's 50 or 100 lines. And so the SDF model actually gets converted to the MicroPython. You thought about it that way? Because that kind of maybe gets the best of, you know, higher power and lower, you know, locality.
Definitely. No, I didn't. I haven't thought about that until now. But
And so
interesting idea. Yeah.
And so the last final sort of question is, did you try an SDF model where, and I'm sorry, I'll get this wrong because I'm, you know, I don't always clue into all the words here. So some of them are, for instance, so you have a light bulb that will go from, you know, that can be dimmed, but in some spaces, you know, 255 is toggle, 254 is full on, and, you know, whatever. And other ecosystems, it's 0 to 100 or something like that. And SDF has some bits to map, you know, those numbers from one point to the other. And did you get into that space of effort, and how well did that work if you tried it?
I probably didn't understand the question too well, but for this proof of concept was part of my bachelor thesis, which is why I've limited it to, in this case, matter as well as lightweight, machine to machine. Yeah.
And it was on, off, and toggle. Those are the two kind
on,
of
off,
operations.
and toggle. Yes.
No dimming. Okay, thanks.
No dimming. This was also because at the time that I built this proof of concept and I wrote my bachelor thesis, Matter was not that mature, especially with open source examples. That's why a lot of them didn't even feature dimming functionality. This implementation that I have right here, this actually also does not feature dimming, even though it could probably. But I think nowadays dimming examples are available for this.
Okay, very good. Thanks, Niklas. Very interesting. One thing I was wondering, like, if I'd like to try your implementation at home, is it possible to run it virtualized, or would you always basically require the microcontroller hardware?
You would. It depends on what functionality. So the microcontrollers are always needed. So these are your typical IoT devices. The bridge would not have to be a microcontroller. It could also be virtualized, as you can build the Matter C++ implementation also for Linux. That should also not be a problem.
Okay, thanks. So I think that could be something interesting for the hackathon exercise, but maybe I'll need to look at hardware shopping too.
I have a small illustration you may want to click at to see what the what Niklas has managed to do here. Not everything has to be run on the bridge. And I think the idea of the bridge actually communicating with some friend in the network that runs the conversion process that are not real-time critical, that should work pretty well.
Then I have one more question on like your experience on using SDF. Like besides the mapping feature that we're still developing, were there any other like extensions that you needed to do on SDF that we should consider potentially to explore?
Not really, no. So
Okay.
SDF, the SDF, especially yeah, the SDF document, especially compared to the Matter specification, was very clear about a lot of things where the Matter specification was not so clear. So yeah.
Okay, sounds good. Thanks.
I'm laughing about that because a lot of the same people were involved in the very beginning of creating SDF that went on and created the Matter specification, including myself. It's great to see that it all worked out because that was really one of the original intentions for SDF, is that it be able to model a more complex IoT device data model like Matter, which is actually mostly 99% the Zigbee model. So the work
Yes.
you've done here could also be applied to Zigbee very easily.
Yeah, definitely. Yeah.
Okay, good. Any more questions or comments before we then move on? And by the way, Niklas, will you be potentially joining the hackathon remotely or on site?
When I'll have to look. Depends on
July.
when the hackathon is.
Okay. The last week of July, I don't remember exact date
The
right now.
last week of July. I'll have to look.
We can check it out
but,
offline.
yeah, but that should probably work. Yes.
Excellent. And I saw still, Jan, did you have a comment or question or?
Yeah, I was wondering, so regarding the ecosystem specific vocabulary, I think you mentioned that you used mapping files, right?
Yes.
Okay, yeah.
Exactly.
And did you also include information about the co-op or lightweight interim server, or is that information only contained in the? Oh, okay, that's only
this
in the
information
configuration.
is only contained in the bridge, and is currently hard coded into the bridge, which could also be future improvements to make this not hard coded into the bridge. Yeah.
Okay, I see. Yeah. But for that, you would also need to extend the vocabulary then, I suppose.
Yeah, definitely.
All right. Thank you.
Okay, great. Thank you. Or Michael,
thank you very much.
I just wanted to say it's great work, and I'd like to, for some of these people in Matter, to see this and maybe try to get them excited about the possibilities.
Definitely. Thank you very much.
Excellent. And yeah, looking forward to if you have a chance to join the hackathon to take a closer look at this there.
Yeah, definitely.
Good. And in that case, thanks a lot, Niklas. And so we can move to our next agenda item. Karsten, please go ahead.
Okay, I have slide control, and MeetEcho, of course, puts interesting messages on top of the slide controls, so you cannot use them. Let me just also say this was a pretty impressive demo, and if you click on the link I put in the chat, this is really what was accomplished here. And I think the last point we got to, how do we get the plumbing going, we are going to look at in a lot more detail in the next couple of months or so, including at the summary meeting in Madrid. So I wanted to give a little bit of an update to a talk I gave in January, where I was trying to partition the work we have been doing on doing the next step from STF base into two big buckets, derivation and instantiation. And the last time I probably didn't talk a lot about the ecosystem perspective, and I want to add a little bit to that as well, but because all these things are so interrelated, I'm probably actually going to talk more about instantiation than the other aspects. So I'm sure there will be a part 3 to this talk. So let's just start with a little bit of a reminder of where we are. So this is one of the original slides of the 2016 IAB workshop that got a lot of this work started. So the idea for SDF is to be this red star that is in the middle of a model translation situation, because we just do not believe we will simply agree on a single standard. So let's make sure that the standard that we are defining, the red star, is really open to doing model translation. And this is based on some pretty well-established hierarchy of doing things, where we have semantic interoperability at the top. So we actually understand what's going on. We have structural interoperability, where we may not understand, but we actually can work with those data and interactions, and we have syntactic interoperability, or at least we can parse them. So that's the background, and we are mostly working on the level of structural interoperability, but of course we will get a little bit more semantic interoperability in there over time as well. And that fits together with the way we have structured the work on data models, where we have information models that are actually on the semantic level and include things like ontologies and taxonomies and vocabularies. We have a data model which provides an abstract syntax, and we have a serialization where we say how actually data is going to be transmitted. And SDF is very much at the data model level, technologically, but it actually serves to do information model work. So that's one interesting thing to notice. So in reality, we are not just talking about data, we are using these data and interactions, and there is not quite such a well-established three-level hierarchy here. But I think every one of us has some basic understanding on how these terms apply to the interaction model level as well. So that's where we are, and we have a document that does all these things. And I think what's really important is that we, in our minds, separate the need to translate data models between different ecosystems, for instance, from the need to translate data between these data models. So if I press my lightweight M2M button, the data that is in the interactions there actually is translated. In this case, the translation is pretty simple because it's essentially both Boolean values. But that's essentially what we want to do in the long term. And that, I think, was part of the question about using dimmers that have 0 to 1 instead of just a Boolean value. So in order to do this, we need to do a little bit of plumbing. So that's different from just SDF base as has been standardized. Before, we need to describe how things are actually working together, the information that Niklas hard-coded in the bridge. So what are we modeling in SDF? SDF base is essentially an interaction model, and it is based on 3 kinds of interactions: property, action, and event. And essentially what it does is for each interaction, it puts it into one of these 3 buckets: property, action, event. And it allows you to define data models of the information that is going into the interaction, the input data, and the information that is coming out of the interaction. So with a property, you usually just read that so that you don't put information in, you get information back. And with an action, you probably have some parameters that control the action, set the dimmer to 0.5 or something. And with events, you again have information coming from the device to the client, but on the device's initiative and not on the client's initiative. So the data model really of these interaction messages is really the core of the specification. And yeah, the interaction model is very simple, just has properties, actions, and events. And there may be a need to add a little bit of an ecosystem-specific detail. So Meta was designed after the SDF design had been done, so they are actually using essentially the same model. But for instance, in Bluetooth, we have quite different interactions, and so we have to make sure that the mapping is described as well. And so we have a concept like protocol binding or mapping that is going into that. Okay, so this should all essentially be just a recap for you. What we are doing here essentially is describing messages, data in flight, and describing when and with what results you can send these messages. And we have those messages at the SDF information model level. And then we have an ecosystem level where these messages might look different. They are not using JSON. They maybe are called commands and not actions and so on. So that's what always needs to be added to this discussion. We are not actually sending around data in an SDF format, because the SDF actually is just a modeling format. It's not a format for actually sending data around. And we do that in the ecosystems. So there's always a translation from the information model that SDF uses to the ecosystem data model. But we are describing it abstractly in the SDF specification in the middle. So you could also say that SDF is all about class level information. It doesn't give you actually information about instances. It just says all refrigerators of this type have a temperature sensor, and you can read it, and all have a temperature set point, and you actually can update that if you want, and so on. So we have the things which have a digital side, which is the side that SDF describes, and they have a physical side, so the temperature sensor is screwed into the refrigerator at some point. But SDF doesn't see that. SDF only sees the digital side. And the digital side is structured into interaction opportunities called affordances. And we have information models or data models for input and output data. And we have some semantic information, for instance, units give meaning to a number. But we are not currently extending this a lot. But we have the capability. What SDF doesn't have is instances. So it always talks about the class, It can store data like links. We have a separate draft for that, which is not yet quite completed, but it should be pretty straightforward. But what SDF describes is how do these links look like, not this particular light switch actually controls that particular light. So we don't have that instance information, and this is why Niklas had to hard code some things there. So let's talk about instances for a moment, because this word can mean different things, and I think we should start by looking what a device instance would be. So an SDF model describes a class of devices, and of course all these devices actually exist and are instances. What the instance adds is its physical presence somewhere, its physical interface. It actually switches on and off the compressor in the refrigerator. There also may be other information that we are not modeling at the SDF level, like the identity of the refrigerator or the address information. What's the IP address? And it turns out that we actually usually use devices together with some other systems that also know something about these devices and actually act for them or act in a way that is relevant about them. So we might have an asset management system, a digital twin. We might have something like the SCIM protocol that we use for setting up and configuring devices, like in the NIPSI work of the ASDF working group. And these support systems actually even might have their own ecosystems. So there is something going on about the device that the device may not know about. Few devices know about SCIM. This is all happening somewhere in the background, in the backend of the network. But the SCIM activity is pretty important for setting up the device and making sure it has the security it needs and so on. So when we talk about a device instance, we have the physical device in mind, but we also have certain physical or logical items in mind that are out there that actually also represent some aspects of this device. So we can talk about device instance information that is not currently modeled by SDF base, some of which may easily be modeled that way, some of which not so easily. That's what we have to find out now. And of course, we also have to think about these things both at the abstract level in which we think about it at the SDF level, but also with respect to a specific ecosystem where suddenly we have something like Bluetooth Max and other things that we have to manage in order to get things to work together. So instance information may include identity information, and identity is a very wide term here. It may include purpose in life information, so that meta switch that Niklas had, that has one purpose, to switch on the lightweight M2M light. So somebody has to tell it that. The device doesn't have to understand the purpose, but the device has to be configured to actually execute that purpose. And then there may be other information about the physical side that the device, that the electronics on the device actually don't understand. So many devices have no idea about their location. Many devices provide some wiring, so there is a relay on the device, but the device doesn't understand what is being switched on and off. There are maybe other manual electrical settings, dip switches, well, those are pretty much dead, but things like that. So the physical side exists, and probably you want to have some documentation about that. And that might live with a digital twin, for instance, or with an asset management system, or possibly even with the thing itself, but usually we try to save the memory that needs. So this is instance information that is not at all about digital interactions. And finally, we also shouldn't forget that to make all this work, it must be possible to associate the device instance with a device model, for instance, by having a link from the instance to the model. So this is what we mean when we talk about a device instance, but this is very abstract. It's a description of many things that may need to work together to actually get this device instance going. So it's not a JSON data structure or something like that. It's first of all very abstract. And now the question is, what can we do with a device instance? And one thing that came up a lot was you actually want to be able to look at it and get its status, all the information about its status or its state. For instance, in order to store this in a digital twin. So we invented this word proof shot for a snapshot of a device that is not necessarily extremely exact, but that describes the state. Like a network management system usually has some parameters that are regularly polled and updated. So that's something that is not modeled by the SDF model, but it consists of all the affordances that allow you to look at the status of the device. So we are not explicitly modeling proof shots. We may be, I have another slide about that. But this is a concept we might want to use when we talk about how to make twins or management instances of this device available. And it turns out those proof shots have a context. So typically they have a timestamp. If you know the refrigerator was on at some time, but I don't know when, that's not very useful. So we always have at least something like a timestamp information in a proof shot, but there may be other context information as well. Okay, and this is, first of all, a concept about properties, but we might want to add something about actions and events later. So please take what you see now with a really, really big rock of salt. This was just an attempt to write down a proof shot in JSON. Actually, this is YAML, but you should recognize this as equivalent to JSON. So we are using the general structure of SDF models, but in this case, we are not using this for a model, but we're using this for an instance. So that's why it says SDF instance at some point. And the instance contains some context information. I have no idea whether we actually want to separate it that strongly from the other information, but let's go with that for the moment. So we have an EUI64 address, which might be the Bluetooth MAC. We have a device name. We have a SCIM object ID. We might have something like a parent instance. So the refrigerator is part of a refrigerator-freezer combination. And the SDF instance might have a model that actually describes it. So it's an instance of the model, well, in this case, of a boat. Yeah, and then under SDF property come all the key value snapshots. So these are not the models, but the actual values. So that would be a working model of something a proof shot could look like. That would describe an instance. It would not provide operations on instances, it would describe an instance. And yeah, we just had a ASTF interim meeting where Jung-Ha and Hyung did provide some information about other proof shot-like structures, like an identity manifest or a context patch. So these are essentially subsets of the information you don't always need all the information about the device. So you may want to get updates only. That would be the context patch, which is essentially just a data structure. So I think that generally fits with the ideas in this talk. So what we also have done is we simply have taken a model and removed all the variability of the model. So instead of saying the temperature can be a number between -30 and +50, we say the temperature is the constant value 1.5, which of course does describe that particular refrigerator that currently is at 1.5 degrees, but it's still a model. So since we don't have meta models, we actually cannot control how such a derived model looks like. And of course, that model may need to be updated. We don't have a good way to handle those updates. So the STF software is oriented towards getting an update from an SDO and maybe even changing the software to handle that. And of course, there is also instance information that is not on device. So as asking a device for what's new may not be particularly useful. So I think this approach was nice for writing some examples, but it's not really the way forward. We really have to distinguish between the models and the instances here. So one important point in general is life cycle, and an important point of time in the life of a device is when it actually is created. So there is something like instantiation going on, and creation, of course, is a multi-step process. So it's not like in a programming language where you say A equals new X and get a new X. You actually need to do a number of things with a device. Solder together, give it power, get a key, and there are lots of things that need to be done here. But generally, just the steps that you need to get an instance actually up and going, I will call those instantiation. So this is not about creating a data object. This is about creating the physical thing with its data interface and all the other components that need to work so it actually can do its work. Now, the interactions are still in the form of messages. So when I set up a key in the device, I probably send it a message, set up a key, and I get back a message with a public key. So those models, those messages probably need to be modeled. So this goes a little bit beyond what we are doing in STF base right now. And one interesting question is there a way to use STF as is to get these messages, or do we have to extend STF? So let me just give one potential outcome. We may at one point decide that instantiation is essentially just another affordance or a set of affordances. So we may want to describe the things that constitute instantiation in the interaction model. But then, of course, we also have to talk about the parameters too. Needed to actually get this instantiation process going. So the one thing we cannot really model here is the existence of the physical device until IoT devices assemble themselves. So we won't have an affordance start to exist. Yeah, so that, of course, raises the question, is there any information beyond STF base? So STF base is all about affordances. and we have recently talked about non-affordance information. Now, much of that should also be modeled by an SDF model, something that might be called an instance model. And if you do this and look at it slightly squinting, it looks exactly like an SDF-based model. So it's not quite clear why it has to be so much different from the models that we have been able to do so far with SDF-base. And if we actually model these interactions properly, then we have a lot of additional control. So what could be different about non-affordance? So maybe we need, instead of a single term non-affordance, we need 3 or 4 terms. One is that a non-affordance, what is called a non-affordance interaction today, might simply be an interaction with an off-device environment, like the asset management system, the SCIM system, the digital twin, and so on. Of course, you should be able to model which of the devices, which of the interfaces you are actually talking to get this off-device interaction going. So something needs to be new here, but maybe not as much as we are thinking right now. There's also information that does not change a lot. So maybe we can, by default, exclude it from proof shots, but maybe we also want to have that information in proof shots. So essentially saying this is information that is static, like the manufacturer's model number and so on, is of interest. Now, static and not so static are probably not just a Boolean thing. We have design time, commission time, runtime things going on. So yeah, that's looking at lifecycle has been something we have been doing a lot. And another thing that may be interesting about one of these not so normal interactions is that they need to be managed in some form. For instance, because we require global uniqueness. So the interaction that gives a device a serial number, that actually has to work in a way that guarantees this managed property. Or getting an IP address also is something of this kind. Not sure whether we will have to distinguish this, but this is again something that might be different. But in summary, what I would say is we probably still can use this really, really simple affordance idea. Whether we call it SDF property or invent a fourth affordance that is describing these new other things, I think that hinges mostly on whether we actually have a good litmus test for deciding which one is which. So when is something a property, when is something this other thing that we haven't named yet, and fully understanding what are the differences. So not just general differences, but something that really requires architecturally different approaches. I think this is what we actually should do next. Okay, so I hope I have intrigued your minds a little bit and given rise to some thinking that could at some point go into the next big step forward for SDF. And I would expect us to think a lot about that at the hackathon in Madrid and at the summary meeting in Madrid, and go forward to solving those problems we're looking at right now. Questions?
Very good. Thanks, Carsten. Maybe one question on the instantiation being affordance. if you go back to that slide.
Which one? This one?
Here. Yeah. So essentially, this would mean that you would interact with an affordance to create an instance, kind of like a constructor in a lot of the programming languages.
Yes.
If that's the mental model here. Would it be that then you get back some kind of a representation of that instance?
Well, that's of course the weird thing, because all the other SDF model interactions assume that you already have a handle for the device, and you use that handle to exercise one of its affordances. And the instantiation is a bit weird, because when you go in there, you have a more weird handle. You don't go in there without any handle. So the programming language A equals new B, that doesn't quite apply. If you think about C++, you would think about actually having an allocator that gives you that device already, except that it's not yet very smart, so you need to instantiate it to actually work with it.
Okay, so subtle differences. I mean, it would be interesting to see like how, a few flow charts with the example, how it would work in practice, but it's an interesting model.
Yeah, and I think we have to have a survey of ecosystems. How do they actually handle this? So what are the interactions that happens to a device that isn't fully instantiated yet? So maybe some devices are always fully instantiated. They leave the factory in an instantiated state. So the headphone that I'm carrying, that probably left the factory with a MAC address assigned and some default passwords assigned and so on. So it can immediately be used. But in other areas, this is not the case. And we need to understand how we would map the ecosystem-specific interactions to this.
Mm-hmm. Yeah, I guess perhaps the live within the bootstrap process, for example, could be thought as one of those. So maybe that's an interesting discussion for the hackathon. Thanks.
Indeed.
Okay, any other questions or comments here? Go ahead, Jan.
I was just wondering, as we are dealing with non-affordance information and in air quotes as a different kind of property, I was wondering whether the instantiation could also be modeled as some kind of action, maybe, that has a different type, or whether we would need a different class of affordance for that. Yeah, or whether we could just reuse SDF action for that, maybe.
SDF action is very general. It just gets some input data and gives you some output data. So you should be able to map a lot of things to an action. The question really is there something about this action which is so different that you want to use a different affordance name for it? And right now, I'm maybe a bit lazy and thinking we might be able to get it done with SDF action.
Great, thank you.
Okay, thank you, Carsten. And now I realize we're actually almost out of time here. We thought we had a relaxed agenda, but actually we had a lot of good discussions. So I think we're gonna need to close here and continue the discussions on the mailing list and in the upcoming face-to-face meeting and hackathon. So unless there are any final remarks from anyone, thank you everyone here, and see you very soon again.
Thank you.
Thank you. Bye.